So let's get going. The speaker for this lecture is Giulio Biroli, whose name has come up in various contexts already, so you probably have a pretty good idea of the work that he's been involved in. So Cooney, for example, mentioned the work on inhomogeneous mode coupling theory. But what Giulio will talk about today is a different end of the business, which is a theory for what happens, what is supposed to happen at further lower temperatures as one approaches the glass transition. So his lectures will cover the topic of the so-called random first-order transition theory.
Yes.
And we're also making a transition for the first
right.
talk using not PowerPoint, but the notepad. So we'll see how that goes.
No, well, not yet. It's not to complicate computation. So I will discuss the general ideas, then some prediction. I will discuss some, let's say, test that the theory has to pass, and some constraint, and then I will end with open questions and puzzles, maybe today or tomorrow. So half of the lecture of tomorrow will be about, again, concluding random first order, and then I will discuss, in the end of my time, length scale. So I will discuss, again, the dynamic length scale in some example, and I would like to discuss more what is the relationship between dynamic length scale, structure, so length scale that you can have from the structure, or static length scale, and what do they mean, because there are many, many length scale in the literature. They all grow, but they are probably very different. So, I try. Okay. Yeah. Transition theory. So this is a theory that has been developed in the 80s by Kirkpatrick, Tirumalai, and Wallines, and that recently has been studied a lot by the statistical physics community. So I don't have lecture notes, but actually I've written recently a review on this with Jean-Philippe Bouchot. Is cited in my abstract. So all the things that I will say today, you can find it there with much more detail. So random first order, I would say, it starts, the starting point is something which is very natural, which I would say is what you would call the Landau free energy, or mean field theory. So what we would like to explain is why liquids, when you cool a supercooled liquid, the system freeze in an amorphous rigid material that we call a glass. So, of course, we would like to know why the time scale increased so much, but at the end, what we would like to explain is this transition to a rigid state of matter, which seems to have no periodic or quasi-periodic order. So let's say the natural starting point, exactly like you do for crystal, is probably to look to the Landau free energy that, I won't define it, hoping that you have seen already. So it's the free energy for a given profile, density profile of the system. Okay? So this tells you what is the free energy for a given density profile. And you know that if you want to study crystal, this is a very good starting point. So Landau used it to show that in higher than 2 dimension, the transition toward the crystal is a first order transition. Then much more recently, there are many theories that has been developed, which goes under the name of density functional theory, that I think you know and that has been discussed by Dasgupta in the previous lecture, that allows you to really describe quantitatively the structure of the crystal at high density or low temperature. So the idea is, similar. So here we have again a transition, like in the case of the crystal, toward the low temperature or high density state, which is a rigid state, in which you seems to break translation invariant. So the idea is, what is the free energy of the system as a function of density? And studying this free energy as a function of density, can we understand why why there is a glass transition and what are the properties of the glass transition? So I will go to the other blackboard, maybe. So tell me if there is one blackboard that is better than the other. Okay. So now when you start to look at the free energy as a function of rho of x, then the basic ingredient of random first order theory is what I would call the complex free energy landscape. Is it okay, or should I write larger? It's fine. Okay, so I think there have been already 2 lectures about this, one by Chandan Das Gupta and the other one by Mark Mezar. So I will just recall what their result was. So the first one, which is, so let's say that I have this f of rho of x. So of course I cannot compute it. I mean, if you give me the potential between particles, I cannot give you what is f of rho of x. Nobody is able to compute it exactly. But there are some approximate theory that one can develop, and that has been developed for crystal, for example. So there is what is called the density functional theory. And I guess, well, and tell me if it's not true, Chandan Das Gupta gave you what is the expression of f within density functional theory. Yes? Okay. So, well, once you take this within this approximation, so within DFT approximation, you have the expression of f, and then you can start to see if there are, well, what the free energy landscape looks like. And you see that actually when the temperature is high, let's say high temperature, let me. Okay, so high temperature or low, so high temperature or low density, so you have just one minimum. So you find, if you just scan, so this of course depends on T and the let's say global density. So if you scan all this energy landscape, you will find just one minimum in which rho of x is just equal to the density of the system, or 0. Okay, so it's a flat profile. But then, well, you find that instead, if you go to low temperature, so lower temperature and high density, then you find many minima. And actually now the minima, rho of x, which I will always put a label alpha, all these minima have a density profile which breaks translation invariance and which is amorphous. So this is the result of, well, minimization, numerical minimization of this free energy f of rho. And then, so this is the first thing, is that what you find from density functional theory, which is an approximation to the true free energy, density free energy function for, let's say, a real system. Then the other thing that you can do, if you are a statistical physicist, is try to look to some very simplified model that you can solve, well, let's say, within some approximation. So, for example, on a very particular lattice, like the Bethe lattice, and then try to study exactly the same thing. And this, I think, was discussed by Mark Mezar. So Mark Mezar, I think, told you that there are many lattice models. So you can find many lattice models. Actually, even some particle model that has been called, lattice glass model, in which you have particles that jump on a side on a lattice with some rules, which looks like reasonable rules. And then in this case, you can compute exactly f of rho. And again, you find that at high temperature or low density, there is just one minimum. But instead, at low temperature or high density, you have many minima. So if I recap, so what has been found is that, let's say here I put an x, which is the temperature, or let's say 1 over the density, or 1 over the pressure. And then there is the regime of high temperature in which I have just one minimum with a profile just rho of x equal to rho 0. And then you start to have many minima. And actually, you can, even in this case, for example, you can compute how many minima do you have. And actually, the number of minima scale with the system size. It goes like exponential, the size of the system times a function, which is, well, you know it already, is what is called the configurational entropy. And now, again, to motivate this, just to say that this makes sense, what you find makes sense, I just recall you what you see in dynamical correlation function. So you know from dynamical correlation function, so let's say, is it okay here? You can see it? So in dynamical correlation function, so for example, the average of rho of Q, so Q is the wave vector, rho is the density, rho minus Q and 0, so this is the dynamical structure factor. You know that, well, these things behave in this way. And then when you, so this is a function of log of time. And so if you decrease the temperature, then you find something which is like this. And then this is the time scale, the relaxation time scale of the system. And now what is this plateau? So what this plateau tells you is that the system, if I start at time equals 0, I know that I have some weird density profile, which is not flat, it's just the configuration at time 0. And then I let the system go, and then, well, the system has some fast relaxation, and then it remains trapped. Well, trapped maybe is not a good term, but it remains in a kind of metastable state in which the density profile is, well, has an, well, if it was in one dimension, so you would have an amorphous density profile, let's say like this, with small fluctuation around, okay? So what this plateau tells you is just that the system, well, there is a separation of time scale and the system remains for a long time in a given density profile. So in this sense, from this point of view, this, well, is not bad. So here, what the free density functional theories tell you is that, well, at high energy, there are so many fluctuations, the dynamics is so fast that you find just one minimum, and then you go to low temperature, and you start to see that there are these kind of metastable states. And actually, you know that, I think this has been discussed, I guess, in the introductory lecture about the glass transition. Of course, this idea that the system is in a metastable state, then it moves to another metastable state, this is, well, an old idea, which is, I think, is, well, it's old and previous to this one. And one, again, can compute the number of metastable states, or at least try to estimate the number of metastable states. And again, there is this configurational entropy that enters that you can measure in experiment via the excess entropy. So the entropy of the liquid minus the entropy of the crystal. Okay? So now, what we know about the configurational entropy? But from experiment or from solution of approximate models or simplified models. Okay, what we know is that here I plot the, so let me define, so the number of, so, okay, so let me think this way. So I have a minimum, alpha. This minimum has a free energy f of alpha. So this is a metastable state f of alpha. I can define his, well, I always write this way the extensive free energy, and this way the intensive free energy. And then, so I can ask how many states with free energy, intensive free energy between f and f plus df I have. And well, this is equal to exponential of v times a function which is still a configurational entropy, but now it's a configurational entropy which depends on f. Okay? And now what is the form of this function? So the form of this function that you get from the solution of these models is this one. So, okay, this is, let me tell you where. So, of course, in the high temperature regime, you just have one state, so there is no there are not many states. Now I'm looking in the regime in which I have many minima, and then I'm just counting how many minima I have in the region between f and, I mean, with free energy between f and f plus df. So this is what you get from the solution of the models. Now, well, okay, let me tell, there is something which is very natural, and something which is just come from the model, and it's maybe wrong. So let's say that I'm here, I'm a state with a free energy F, and so why the entropy should behave in this way? So, well, of course, if I want to find, if a given temperature, I want to find states which have a lower free energy. So meaning that I have a lower free energy, if I have particle which is interact with a given potential, it means that probably I don't have just to, well, I have to put, if I put the particle here, so I have to choose carefully where I have to put the other particles in order to have a very low energy configuration, okay? And so the lowest is the energy that I want to get. The more constraint I have, so I have to put the next near neighbors here, and then the other here, and then the other here. Instead, if I want to have a high energy configuration, maybe I will optimize just close to me, and then, well, I will do something else away from it. So the more constraint I have, so, well, the less freedom I have, so the less, well, you can think that the less state will I have. So this will go down if I want to reach state which are very well optimized with very low free energy. Instead, this will go up if, of course, I want to find state with high energy or high free energy. And well, at a certain point, well, you can think that this has to stop, just because, well, if I want to, I mean, if I have a certain interaction, I cannot find stable state with an extremely high energy, which, well, fluctuates around a given amorphous profile. Just because the particle, to have a high energy, the particle have to move so much, you have so much fluctuation that you cannot sustain this kind of profile. And so you expect also that this will stop with some free energy, which is called threshold in the literature. And then, well, okay, then there is a big question, which is, well, okay, then this will go to 0 at a certain value, f min. And then, well, let me discuss after the way in which it goes to 0. So for the moment, I think this is very natural and will be also true in many models, not just in glasses. Okay, now something that I think, again, Mark have told you. Well, we'll do it here. Oops. So let's now do the thermodynamics of this system. So what we have learned is that there is, let's say, below a certain temperature that we can call onset temperature, the system, well, say, quote unquote, jumps between different metastable states. So if I look to the thermodynamics of the system, so it's natural to sum, well, I have to do the partition function, so I have to sum over all configuration, and now I can rewrite the sum over all configuration as the sum over all configuration which belong to a state alpha, and then plus the sum over all configuration which belongs to the state beta, and so on and so forth. So this means that I can rewrite this, let's say, sum over all configuration of exponential minus beta h c, just like the sum over all states alpha that I have here, times exponential minus beta. So beta is the inverse temperature, is 1 over t, f of alpha. Okay? So I'm just saying that, let's say that I have a potential which is like this, which of course it's a cartoon, because this I have is just, well, I have just one dimension here. And I'm saying that the system is vibrating here, then sometimes it goes there, then sometimes it goes there. So the majority of time it stays here or there or there. And so I do just a restricted sum inside here, and this gives you exponential minus beta of alpha. Okay, so this is alpha 1, alpha 2, alpha 3. Okay. Now I can try to make progress on this expression, just rewriting, and now I will rewrite it here. Yes? Yeah, good question. So we always say that there is a, well, we don't know if there is always a crystal, but we can say in many cases there is a crystal. So it means that here there is a whoop, a low, much lower minimum, which corresponds to the crystal. But actually, well, the, let's say, a big conjecture is that the dynamics of the system is always restricted to this region. It never looks to the crystal. And so what I want to do is to describe the physics of the metastable supercooled liquids, which just wanders in this region of phase space. It never goes here, and actually if it goes here, then the system crystallizes, so, well, you're not explaining the glass. But, well, that's a conjecture. Of course, if you start to have some small crystallite in your liquids, then it might be a problem. But no, that's an hypothesis. So I'm just forgetting the crystal. Yes, yes. So what I define is really the complexity. And then, well, this all goes also under the name of configurational entropy. So what you may, in general, in experiment, you say, sometimes you say that you measure the configurational entropy, but what you measure is the excess entropy, and you think that this is a good estimation for the configurational entropy. So for me, configurational entropy or complexity are the same thing. Sorry, it's not, so I will go, it's okay? So because what I've done is, so I sum over all configuration exponential minus beta h. And then what I can do is that, well, I restrict the sum in this way. Here I sum over states alpha, so alpha 1, alpha 2, alpha 3. And then I sum over all sorry, don't say it. Well, so I sum over alpha, and then I sum over all configuration which belongs to alpha, exponential minus beta h. And this thing is just the definition of exponential minus beta f alpha. Okay, so, well, I will go there. when did I start? Okay. 25, so okay, so you should stop there. Okay, so now, so the configurational entropy, I will draw it again as this form. And now, so I just computing the partition function, sum over alpha, exponential minus beta f of alpha. And thus I can rewrite this as the integral over the free energy, intensive free energy f, and then here I put all the number of all states with intensive free energy f times exponential minus beta f times the volume. Okay, this is just a way to rewrite this sum. Now, well, now I know what is this. Well, it's just the complexity or configurational entropy that I introduced previously. So this is going to be equal to exponential of SC of f times v minus beta f of v. Okay, so I can put v, plug out the v, so I have this term. Now, well, this is the partition function. I'm considering a v which is very large because it's a macroscopic system. So of course this integral can be done. It's just dominated by the maximum of the term which is inside the parenthesis. So what I have is now that I want to compute the log of z divided by v, which is just minus beta f. So the partition function, so this is the free energy of the real system, of the entire system, let's say the supercooled liquid, which is log of z divided by the volume. And well, this will be just SC of f star minus beta of f star, where f star is the value for which this function has a maximum. And if I write down what is this, well, the condition to have this, I will get that f star verify this equation. Okay, I just take the derivative of this expression. So this is the equation verified by f star. And actually, I can solve this equation just graphically. So what does it mean is that I have this SC of f between f min and let's say f threshold. And I have to find the value of f at which the slope here is equal to beta. So where beta is the inverse temperature. Okay? So this is beta, the slope equal to beta. So what happens now? So if I decrease the temperature, beta increase. So the slope becomes larger. So I'm going down in free energy, which again, it's normal because you decrease the temperature, you want to explore states which have lowest energy, and so what you want to do is, in the competition between energy and entropy, well, it's energy that wins, and so, or free energy, and so you go down, okay? And then, well, there are two characteristic temperatures when you do this. There are one temperature, which is the temperature at which the slope is here, which is called beta k, equal to 1 over tk, where tk stands for Kaufman. So it means that, so now what does it mean? It means that if I change beta, so the configurational entropy of the system as a function of temperature is just equal to the configurational entropy of f star, okay? Where f star depends on beta. So I decrease the temperature, which means that I increase beta, f star decrease, and while I'm going down here, so the configurational entropy is decreasing, and it becomes 0 at the temperature Tk. Okay? So this is the first important result that I think, again, Mark discussed already. So at Tk, the configurational entropy is equal to 0. And, well, and then the other thing is that, well, when T goes to Tk, the configurational entropy goes to 0, well, just linearly, like T minus Tk, with some prefactor in front. Okay, that's the first thing. So I think, yeah, well, you have already seen, there have been, I think, already discussion about the Kaufman temperature and the fact that there might be a temperature at which the configurational entropy goes to 0. And so this is the way in which you find it in this model. And then the other thing which is important, and that I won't discuss in detail, actually, is, well, there is a temperature at which I'm here. So at which, such that, well, this is called the mode coupling transition temperature. So this would correspond to beta MCT. So it's the temperature such that if I go to higher temperature, there are just no more metastable states. And while this is a temperature which is related to the mode coupling transition, and I think will be discussed in the next lecture tomorrow by Bhattacharya, and I won't discuss it. So actually, what I will focus on today is really what happens close to TK, and so close to the point at which the configuration entropy is going to 0. Okay, so this is something that I think you have seen already with Mark. And, well, maybe I don't know if you have questions. No? Okay, so there are, I think, two things that I would like to say. The first one is that all these things, until now, to me, looks very, very reasonable, except one, which is that it exists really a temperature Tk at which the configuration entropy goes to 0. See, this is clearly an extra assumption. Otherwise, I mean, the fact that there are many minima, well, that's probably sure. You can see it in many, many different ways. The fact that there is an exponential number, well, again, it's true. You can see it in many, many different ways. The fact that, well, their configuration entropy goes, well, decrease when you decrease the temperature, it's true. So all these things, I think, are true in general. But the fact that, well, there is a definite transition at which Tk, with Tk different from 0, at which the configuration entropy goes to 0, then, well, this is something which comes from the model and which is non-trivial and which is, of course, an assumption of the theory. Okay. Here? Yes, but this, I think, it's a less strong assumption in the sense that if I mean, it's difficult to think that I will going to find states which are metastable, so which are stable on a certain time scale, if I'm looking at extremely high energy. Because how are you going to create this extremely high energy? I mean, I will have particles that fluctuate. So this, I mean, the fact that there is an instability at a certain point, it looks more reasonable than this one. But, well. Yes, if you just look to the minima, yeah. Well, but even in terms of free energy minima, right? I mean, if I just tell you, try to find free energy minima with extremely high energy, well, you don't find, right? I mean, there is an energy above which you're not able to find minima anymore. I mean, or at least it seems reasonable that there is an energy like this. Is pushed very high, okay. Okay, so it means that this slope is flat at that point, okay. Okay, and then, so these are the things that I wanted to say. So, well, the other thing, of course, is that for the moment we have just discussed about the statics, and really what random first order is about is try to describe the dynamics, and this is what I'm going to do in the following. And the other thing that I would like to stress is that, well, again, here you have really an exponential number of states. So this is something, well, random first order is a theory in statistical physics that try to handle a problem which is quite unusual. So in general, in phase transition, you just have one minimum or a few minima in the free energy landscape, and you can understand the phase transition in terms of, well, of this minima. And here you have an exponential number, so, well, you have to do something else. And this is also why random first order is not a completely developed theory. It's something which is, well, quite unusual and difficult to treat. So now I would like to try to understand or discuss, well, the dynamics between states. And so, well, I will go on there again. So there is no hope of having. Nice. Okay, so I think I saw the slides of Marc Mézard, and I think he already told you something about metastability. So what I want to now to try to understand is what is the dynamics between these states. So I say that during the dynamical evolution, I just draw this cartoon in which the state stays a little bit here, then it goes there, and then it goes there. So how this really works, and how this works in real space, this is the question. And so the first thing that I think Mark already told you is that if you take a state alpha, now in general, when you look at the problem in statistical physics, when you find the minimum of the free energy landscape, this is a phase of the system, meaning that the system can be there at low temperature and can stay there forever. Instead here, well, we find minima, but we know already that these minima are just metastable. And how we can know this is that, let's take a state with alpha, with a free energy f of alpha. And while it's very simple to show that this state f of alpha will nucleate inside state F gamma, where F gamma is less than F of alpha. And this, I think it was in one of the slides of Mark. And the idea is the following. So I have a state alpha, let's say that it's here. I know that if inside I put a bubble of the state gamma, so it means, for example, let's say in a numerical simulation or a Gedanken numerical simulation, I take all the particle here in the state alpha, I put the particle away, and then I put the particle back exactly in the position that they would have in the state gamma, okay? So if I do this, then I know that, well, I will have a gain in free energy, which is just F of gamma minus F of alpha times R to the D, where R is the radius of this droplet. And then I have a loss term, which quite generally is something which scale like, let's say, surface tension times, I would say, RD minus 1 in usual nucleation theory. Then we will discuss this again. But in usual nucleation theory, I would have something which is like this. So I gain and the loss. And if R is large enough, then the gain term will win. So it means that in my system, if I think that the system is in the state alpha, there will be droplet. And, well, if I just write down what is delta F of R, which is the gain minus the loss, this has this kind of behavior, as usual in nucleation problem. And so you see that, well, it increased, but then it decreased, meaning that if I call this the critical radius of the droplet, so I know that the system in the state alpha will nucleate some droplets, which, well, they can increase until a certain radius. And if the radius is less than RC, then the droplet will disappear. And if the radius becomes larger than RC, then the droplet will invade the system. So there is a finite time to go from alpha to nucleate the state gamma inside alpha. So while alpha cannot be stable, cannot be a stable state, it should be metastable. And we see already that it will go to states like gamma. But now the strange thing is that, which makes the problem a bit difficult, or at least it makes the problem difficult for certain times, is that, well, we discuss, I don't know if you know this or the other blackboard, that, well, if I compute the partition function of the system, sum over alpha exponential minus beta f of alpha, this is dominated, this sum is dominated by states which all have the same free energy, F star, intensive free energy F star. So it means that if I take the system, while the system is in a state alpha, which has this typical free energy F star, okay? So in a certain sense, it's strange here because I'm saying, well, the state alpha is unstable because it will go to some state gamma, but at the same time, while the state gamma, which has the lowest free energy, well, are very rare inside, well, in the Boltzmann measure. So, well, this is the first puzzle, and, well, I will just tell you just to make you think a little bit about this. And then, well, so the other possibility is that, well, actually, if the system is typically in free energy state, which has a free energy F star, so what I should think about is that the system is moving between state with free energy F star. But now, well, it comes a problem because if I want to describe the dynamics between states, let's say F alpha 1, F alpha 2, F alpha 3, and all these states have all the same free energy, now, well, my argument, my nucleation argument doesn't work anymore because the gain term is completely lost, and I just have the loss term, so I won't nucleate a state alpha 1 inside a state alpha 2 if they have the same free energy. So, well, that's the other thing which is strange. And then we have to understand what happens and why actually the states, the system goes away from the state alpha. And so this is exactly what I'm going to do now. I just checked that I did all the things that I wanted to do. So maybe I can just put here for reference a recap on the temperature axis. So we say the temperature axis, we have a temperature, let's say here, which is TMCT, which is a little bit vaguely defined. Here I have just one minimum of the free energy of one metastable state with rho of x equal to rho 0. Here I have many, meaning an exponential number. And here I have a temperature T of k in which the configuration entropy goes to 0. And now for the moment we want to describe what happens to the dynamics here. Okay. Other questions? Well, no, just the first puzzle is that I see that the state alpha is unstable because it can nucleate state gamma. But the problem is that I also say that when I do this sum, all the states which are here are the same free energy. So, okay, I find a way to escape to a state which is very rare. So, well, this is a bit strange. Okay, so yes, so what I said is that, so there is, as I discussed, there is a configurational entropy here. So there are many states with different free energy. But the one which dominates the partition function, so the one that you see at equilibrium, which you see with probability 1, they always all have the same free energy, which is given by F star. So what I have to understand is actually the dynamics inside here, inside all these states. You see they have all the same free energy. It's not clear why I should go from one to the other. I mean, it's not this nucleation process, at least. But it's, well, we think it's some kind of nucleation process. So, okay, now I will tell you what is the idea.
So let me see if I understand that. The question then is, I have many minima with F star.
Yes.
And how does the system do that?
Yeah, and also I think what these minima really are, especially in real space, and what does it mean that I move from one to the other. Yes. Okay. And actually, well, I will tell you what are the things that one can do properly and what are the things in which remains unwavering and afterwards, maybe tomorrow. And I will also tell you what are the things which are well-defined and what are the things which are not well-defined, because unfortunately there are. So now here, okay, so the idea is that I have these states, alpha, which again, in a real phase transition, this will indicate a phase of the system. So I don't know, a BCC crystal, for example, if I do density functional theory. But here the strange thing is that I have many of them which correspond to many different amorphous density profiles. So now I would like to try to understand that why these states, alpha with a free energy f of alpha, are not real phase of the system. And what I will end up, which is something which is called the mosaic state by Kirkpatrick, Tourmalin, and Wallines, and which actually maybe I like to call a microphase separated state. With many phases, many phases. Okay, so the idea is the following. Let's just try to think if, well, these were indeed a real phase of the system. So if this is a phase of the system, well, I can take the system inside this phase, alpha, and then, well, if it's a phase of the system, so what one thing that I can do is that, let's say that I do a numerical simulation, so I have particle here which moves, and then I freeze all the particles which are outside the cavity of radius r, okay? So if it's a phase of the system, well, what I'm going to do is that I'm going to do, again, the thermodynamics of this cavity, so Z of the cavity, partition function of the cavity, with the boundary condition, which is fixed, and is given by a configuration C, which is in the phase alpha, okay? So what I do is really, well, I equilibrate the system. If the system is the state alpha, I just freeze all the particles outside the cavity, and then I run, if you want, a code again in the numerics. So I just do the thermodynamics again inside this cavity with this boundary condition. And well, if it's a real phase, what I should find is that inside here, I should find the same phase which is outside. This is what you find if the system, for example, freezes in a BCC crystal. While you fix the particle outside in a BCC crystal, you redo the thermodynamics inside, and you will find the particles that are again in the same configuration from which you start to the dynamics. So if I do this, and I just redo the same sum that I did at the beginning, so exactly the same idea. So what I have again just a sum over all states, alpha. Call it alpha. And now, well, no, sorry, I call it beta. No, beta is another one. I call it gamma. Then sum over all states gamma. And now I have to do, there is a difference, whether I take all gamma, which are different from the state alpha, and then there is a contribution which is due to the state alpha. So the contribution which is due to the state alpha is just exponential minus beta f alpha. So, sorry, f alpha r to the d, okay? Now, if I sum over all the other states with the states gamma, so what I have here is exponential minus beta F gamma R to the D. And, well, there is another term here, which is the fact that when I put here a state which is gamma, which is different from alpha, well, I have two different phases. So, well, I will have a surface tension between the phases. Just the system is going to tell me I don't want to be in the state gamma because it doesn't have the good boundary condition with the state which is outside. So I will pay some energy, which is again is a loss term that I described before, which will be a minus beta, or let's say epsilon r to the theta. Okay, now I'm just general, just because we don't know exactly what's going on. So I just put an exponent theta here. So in general nucleation problem, theta is equal to d minus 1, which is just this the dimension. So it just means that it's proportional to the surface with the system, the surface with the other phase. And now I put theta just by generality, and I will discuss more later what does it mean. So now I have these two terms. Well, I have to do again the sum. And, oops, no. And so if I do the sum, remember what I should find if the state alpha is stable, I should find the state alpha again inside the cavity. So now if I do it, so of course, I'm consider state alpha with a free energy f of alpha equal to f star. I'm not going to consider states which are which are not probed by the equilibrium measure. And well, so now I can again rewrite this sum as an integral. So it's the integral of all states, well, let's say different from alpha, which have a free energy, density free energy f of alpha. So it's again n of f exponential minus beta f r to the d. And then there is this term which is minus beta epsilon r to the theta. And then there is the other term, plus exponential minus beta f star r to the d. Now, well, here I can do exactly what I've done before. So just do a saddle point on f, because I can replace this by exponential of sc of f r to the d. It's okay, you see, or it's too small? It's too small, or it's okay? Okay, bit high. Okay. So this one is exponential r to the d plus sc of f. So I can just do exactly what I did before. If the cavity is large enough, we are going to think that we look on large length scale. So this factor in front of here and in front of here is very large. So I just to do exactly the thing that I did before with v, which is just equal to r to the d. And so I get that this partition function is equal to exponential minus beta f star r to the d. And then I have two terms. So I have one here, which is just this term. So this comes from here. And then here, what I have, well, I have exponential sc f star r to the d minus epsilon beta r to the theta. Okay? Is it okay? So I just collect exactly, I just did the same thing than before. So before I just got these two terms. Now I have also this surface tension. And well, I now have these two terms. Okay? Questions? Okay. Okay, so now what happens is that if I want to understand what's going on in this partition, in this sum, so I have these two terms. So you see, I have a competition between these two terms. So I know that if r is small, so while theta, as I told you, theta, let's say it's always less or equal than d minus 1. This is the dimension of the system. So this means when r is small, this is the term which is going to dominate, especially because I'm going to look to see in cases in which SC is small, so close to TK. So this is small. When r is large, so when r is small, this term dominates. It's much larger than this one. But when r is large enough, this term will be larger than this one, just because here I have a d and here I have a d minus 1. So this means that if I look to this term, this will be much smaller than 1 for small r, and will be much larger than 1 for large r. And there is a crossover length that you can compute. It's just given by the competition between these two terms, which is xi, psi, which is equal to so epsilon divided by T, so T is the temperature, Sc of F star, 1 over d minus theta. So if R is larger than psi, So what happens? So, okay, I just draw again the cavity here. I have the state alpha outside. So if, well, I have two things. So if R is less than C, so what happens if R is less than C? So if R is less than C, this is much smaller than 1. This is the term that dominates. And this means that inside, actually, I have a very high probability to have alpha again. And instead, if R is much larger than psi, then this dominates. And then, actually, with very, very high probability, I will go into another state, gamma. Okay? And again, well, this is natural in the sense you just, well, if you want, don't think to the math, just think to the physics. So what this is tell you is that if the system, so I have a loss term, which is the fact that if I put inside the same state, a state which is different from the state which outside, I will pay some energy, which is the surface tension energy. However, if the system, well, I can gain something because I can choose many different states, so there is an entropy that I can gain. And of course, the entropy, well, for large system size, will always win because it's extensive compared with other term, which is just proportional to the surface. So no matter how small is S of C, well, at the end, I will just go into the other states. So this means actually that if I think in terms of phases, well, it doesn't make sense if I go to length scale which are larger than psi. So for length scale which are smaller than psi, it's true that the boundary will fix me the bulk of the cavity, the interior of the cavity. If I go to length scale which are larger than psi, then, well, there is so much entropy that the system will just choose another phase. Which one? So here I have a plus, here I have a minus. Sorry. This one? This one? Yeah. So let's. Yes. Yes, Gilles.
Now, you basically, your calculation relies on the fact that there's no free energy cost when you have another configuration belonging to state alpha inside.
Yeah, what this
is this reasonable, or
that is? You mean just because I fix the configuration? Okay.
You fix one configuration of state alpha outside. Now imagine I have inside another configuration of state alpha. Why isn't there a cost between those two configurations?
Well, okay, so, okay, this is not a simple question, but so what I have to say is that, so if I it's true that if I freeze the particle, then I do the thermodynamics inside, then there will also be a loss term, just because I froze the particle. What I should do is that I should put a constraint in such a way that I let the particle vibrate, but have the density profile, which is exactly in the same state alpha. So I mean, actually, the condition is that outside the cavity, I have the density profile, which is the average density profile, which is equal to alpha. And I have to let the system fluctuate, otherwise I will lose. But I will try to, I mean, here, it's clear that the definition what alpha is not clear, and I will discuss more tomorrow what really we mean by alpha. But for the moment, I will just be end waving. Yes? Yes.
So what is that e power minus beta f star rd? Where does that contribution come?
This one?
The front of the bracket.
This one.
Yeah.
Okay. So
where does that
this term, well, it just comes from. I have it here.
Yeah, that term.
And I have it there.
No, the plus. Yeah, the second term of this first equation.
Yeah, the plus one is what is that.
The plus one? Yeah. Oh, it's just this one. It's this one.
So, but you're only writing it for the cavity, right?
I'm writing the partition function from the cavity, and then here I just put in all the contribution from all states which are different from alpha, and here I put in the contribution for the state alpha. Yeah. And I'm just looking to the competition between the two.
So I have two questions. First is that in case of nucleation theory, when there is competition between two terms, I mean it's you take when you take the derivative with respect to r of that, but here you are.
Yeah. I should put, well, the length is always defined up to a proportionality constant. So, well, if you want, there is a numerical factor here, which just comes from, well, really, the value of r when this thing becomes larger than 1. But, well, if I just, so here is a number that I'm not putting.
No. But you are actually equating the exponent to 0. You are not calculating the maximum value of the, I mean, which one is?
So I'm just looking to the value of r where this is equal to this.
Yeah.
Just because when r is larger than this value, then this will be larger than this one. So it will be larger than 1.
So my question is that why you are not looking at the value of r where this term is maximum?
This term?
The value of r the exponent is maximum. I mean, as a function of r.
Yes. So let me see if I understand. So you want to find the value of r where this is maximum,
yeah,
and then find the value of psi where the maximum is equal to, well, the maximum is equal to 0, right? That's the thing. And so what you say is that I should find the maximum of this, and then look when the maximum becomes larger than 0, because then, well, these things will so what do you mean, the maximum with respect to r?
Yeah, no, yeah. What I'm saying is that you can also find the, I mean, the exponent is a function of r. It has two terms, r to the d and r to the theta. Yes. So you can also find the value of r where this exponent has the maximum value. Meaning the DDR of the exponent is equate to 0, and that also you can call it xi.
Okay. Yeah, I agree. And will be equal to this?
No, it will be something different.
No, up to a constant.
Up to a constant it will be same. But you are not doing that. So
no,
what
just
is the
because
physical reason for
no, because I don't care about the constant for all the things that I'm doing the following. So you're right, there is a constant here, but I'm just sloppy with the constant. I just want to actually the only thing which it's important to me at this moment is what is the dependence on the configurational entropy. So, we can discuss later, but if you do the maximum, you find exactly this expression, except if I did something wrong, times a constant. And since I want to know what is the behavior of psi as a function of the configurational entropy, then it's okay. Yes.
Okay. So this determination of the length scale is the answer to the question that you posed, which is beyond what size does the probability weight for the set of all other configurations with this free energy become bigger? But if we go back now to a supercooled liquid, right? I mean, how should we interpret this? Because if you think of this as Shilatya was saying as a nucleation problem, then you expect this to grow.
Yeah. So
if I think of this as a critical
now I will just discuss really what the mosaic state is, and I will address this question. But maybe I mean, if you have a question along the same line, maybe it's better that I say what the mosaic state is beyond this math, and then we can ask questions.
No, I think I have a more basic question.
Okay.
So I guess the thing I'm not understanding is you're saying that I have a lower free energy for the nucleated state because there are many possible states I could have chosen. But then at some point you have to nucleate one of them.
Yes.
Right? And that particular state doesn't have a lower free energy than the surrounding phase.
Not that one.
Not that one.
But the fact that you can nucleate any one of them, it just makes you go away. Then you don't come back. I mean, it's just because, well, what I'm doing here is just I fix here, I do the thermodynamics inside. So I know that if I have a high probability, what happens during the dynamics, if you want to think in this way, if I fix the boundary, so what I have is that I have the state alpha inside that equals 0, then it try to go away, then it go away, and then actually there are so many states that then from that state you go to another one, then to another one, and since there are so many, it never comes back if the cavity is small enough.
Okay.
So that's a dynamic way to tell you that the entropy, since there is an entropy, there are so many minima that once you escape, you never go back.
Okay.
Which is
That's when the cavity is large enough, right?
wet when the cavity is large enough. Okay, so maybe now I will describe a little bit more what is the mosaic state. How much time do we have? How much? 30, 20 minutes. Is it bad, the blackboard? Or yes, I should try, just to make fun of me if I don't succeed. Okay. Okay. Okay, so the property of the mosaic state. It's too small? It's okay? Okay. So now I would like to discuss the property of what I call the mosaic state. So what I describe here is just I fix the boundary and I do the thermodynamics of the cavity. Now I would like to try to describe what the supercooled liquid is doing. And so here, that's maybe a conjecture if you want. And the idea is the following. So the fact is that the supercooled liquid will be in a microphase separated state, okay, which I will draw in this way, in which inside here I have, let's say, the phase alpha 1, here the phase alpha 2, here the phase alpha 3, here the phase alpha 4. And so the typical length of this is psi, which I determine already. So because what I found before is that if I have on length scale smaller than psi, well, I really want, the boundary really fix me the bulk, just because otherwise I pay too much in surface tension. But beyond this length, I have so many states that once I go away from one state, I never come back. So here I have alpha 1, alpha 2, alpha 3, and alpha 4. But then, of course, well, the supercooled liquid is ergodic, if you forget about the crystal. And so the state alpha 1 then will become alpha 3, if you want, and alpha 2 will become alpha n, and so on and so forth. So there is a dynamics between the state. For the moment, I'm not addressing. So for the moment, it's just, let's say, a static picture. So this is what I have, the state. So the system is in a mosaic state. So now what are the thermodynamic property of the mosaic state? So if I write below, or no, maybe. Exactly. And the idea is that the liquid is simple, is a stupid liquid with no correlation above this length psi. And below this length psi, well, it's in a let's say, particular microphase with particular static correlation. But above psi, well, no correlation at all. So this means, indeed, now that I can write below. Okay. So now if I want to compute the free energy of the system, so free energy divided by the volume, well, what I have to do is to write the free energy of, let's say, one blob. So just one of this part. So this is the free energy of one blob times the number of blobs. Sorry, maybe I will do it like this. So the global free energy is the free energy of one blob times the number of blobs. So the number of blobs is the volume divided c to the d. Okay, this is just the number of blobs that I have. And then, well, the free energy of one blob, so what is it? Well, we know what is it. It's just c to the d times f star. So divided volume divided by c to the d. So the 2c to the d goes away. And then, so I have the extensive free energy of the system is equal to f star times v. So the free energy now, intensive free energy of the system is equal to f star. So, well, it's a kind of miracle, but you find that. So now it looks like, well, we find exactly the same free energy that we have found at the beginning without thinking about nucleation. So the free energy of the global system is equal, sorry, okay, I'm using the wrong notation. So let's say F star bar. This is the free energy of one given blob. And we know that the free energy of one given blob is equal to F star, the one which realized the maximum of the entropy, minus the configuration of the, well, of the integral that I described before. Okay, I hope this is clear. If it's not clear, just tell me. So so the computation that I've done before is that, well, inside one blob I have this, and then here I'm just saying that the total free energy is just the free energy of one blob. Okay, and well, there is one term which I'm missing, which is, in principle, I found that there is some surface tension because the system is broken up in many different pieces, But well, this term is, let's say, a subleading term, which goes to 0 because it's a order of 1 over c to some power. So when I approach tk, this will go away. So there is a correction here, but for the moment I don't wonder about the correction. Okay, so this is one thing. And then the other thing that I want to discuss is that this length psi, which is well, it's just because I say that, well, one blob for me, well, to me, so if I take, so let's say, I replace the entire system by a sum of an independent subsystem. And then I compute, a subsystem is a system of site psi. And then I compute the thermodynamics of a system of sites psi. On the site psi, I can do mean field theory, it's okay. Because, I mean, the system, I mean, the states are well defined on the length psi. So I'm just saying that the, let's say I have an extensivity property to compute the free or total free energy is that the free energy, the entire free energy of one blob. And on this scale, I can do mean field theory. And within mean field theory, I just get this result.
But then what you showed, the little picture that you drew, is not a snapshot of the system. You're assuming that the blobs are staying there for a while, and that inside the blob you can sample all the states. Yes. This is why you gain the entropy. So the blobs have they stay.
You mean they stay?
They stay for a while. That is, the structure you have, the blobs are almost permanent in this calculation.
No, why? I don't understand. So I'm just saying that, I mean, one of this blob is like a mean field system on this length. And then, so if I look, the mean field system is in a state alpha for some time, then you go to another state, alpha 2, and then to another state, alpha 3. And if I want to compute the thermodynamics of this, well, I have to sum over all states. So what I'm saying is that, so this is a snapshot, then I let the dynamics go, and then I have a state alpha 4, which goes to another state, which is just another independent state. I have the same thing here. So they are just moving, and so it's just a small mean field system.
I guess, I mean, as I understand, what Gilles is asking is, if you want to include that entropy term, you have to look at the system on a time scale over which the mosaic structure averages out.
Of course. Otherwise, I'm not computing the free energy of the supercooled liquid. I'm computing the free energy of, let's say, the metastable state on short time scale. So it's true. Yeah, I have to wait enough time so that the mosaic will just change state. Yes. No, so alpha 1 is just, so there is a portion of the system, subsystem, in which, let's say, you have a given density profile, which correspond to, let's say, well, okay, now I'm a bit sketchy, but which correspond to one minimum, okay? And then you have another one, which is another minimum. Actually, this is not very precise, and I will discuss more of this tomorrow. But what you have to think is just that, let's say, when you look at the minimum of the free energy density, you find different good configuration, and here is just a snapshot with good configuration, but then when you let the system evolve, so we'll go over on the other configuration. And so, yeah, so the last thing is that, so the length, as I told you, is epsilon t as configurational to the 1 over d minus theta, which means now that since the configurational entropy goes to 0 linearly at tk, so the length is going to diverge at tk. So this really means that the more we approach to tk, the larger are these phase. And actually what happens at tk is that the system really has a phase transition at this point toward one of these states, one of these amorphous states. So within this theory, this is a theory for a transition to toward an amorphous state of matter, in which at tk you have an infinite correlation line. Okay, so far.
Excuse me?
Yes.
So this F star bar is the free energy density of the entire system. Is it correct?
Yes. This one is the free energy of the supercooled liquid.
Okay.
Neglecting the crystal.
And these alpha 1, alpha 2, the regions that you considered, they are, I mean, one region is completely independent of other region, is it?
Well, that's the idea, yeah, is that above the scale, psi, you have independent subsystem, which I mean is just what you have in. I mean, there is always in any system a given correlation such that above this correlation length you just can and you just have independent subsystem.
So then, is it possible to write down the free energy of the whole system as sum over free energy of all these alphas? I mean, is
yes,
that what you are doing?
is exactly what I did. So I say that the free energy of the system is equal to the, well, maybe this is related again to the question of Gilles. So what I'm saying is that here I have the free energy of one of the blob times the number of blob. And then the free energy of one of the blob, well, I just have to take a subsystem of psi, and then sum over all states that I have, and then I get just the mean field result, which is this one.
But I look at all the different metastable states it can sample, I get this free energy, right? Which is F.
Yes.
But now if I break it up into the mosaics, and in each of the different mosaics, I let the system sample all the different states, and I look at all the combinations, I'm again ending up with the same free energy.
Yes.
It looks a bit funny.
It's just, okay, now maybe, okay, I will discuss this point tomorrow actually. It's again what really we mean with alpha, with the state alpha. Okay, so, well, just to finish on this, so what we have found is that, so now we have a mosaic state, which is, let's say, microphase separated with many phases. Actually, the supercooled liquid is continuously evolving between this phase on this landscape psi. This landscape psi actually diverge as 1 over T minus Tk to the 1 over d minus theta, okay, when you approach Tk. And so far we are still at the static level. So this just imagine what happens at the static level. So now at the end we should arrive to what happens at the dynamics. And I have to say that until this point, I think the things are quite reasonable, and they can be probably, well, not proved, but you can do quantitative argument to show, well, and let's say microscopic computation to show that these kind of things are reasonable and that they can happen. Now there is a big step, which is what happens now to the dynamics. So how can I describe the evolution from one, let's say, the relaxation of the mosaic state. So now it's dynamic. And here actually there is nothing more than end-waving argument beyond this, I would say. So I have, again, alpha 1, alpha 2, alpha 3. And again, the idea is that to understand what happens to the relaxation of the system, I can, again, just focus on the system on the side psi, and I have just to understand, well, or guess, how I can change from state alpha 1 to another state. And here one just do an assumption that I can try to argue a little bit that is correct, but, well, there is no strong argument, is that the time scale now to go from one blob to the other is given by exponential times, let's say, a barrier, which depends on psi, divided by the temperature, okay? Now the barrier, the assumption is that the barrier goes like the length psi to an exponent psi. So why people think about, well, why this choice? So, well, the idea is that, so from mean field theory, I have all these phases, and actually I can compute the stability of these phases. So these are stable, looks like from mean field theory, these are stable phase. So in terms of rigidity, for example, I can compute the shear modulus. These have a finite shear modulus. This looks like real stable phase. And this, so what I have here, so when I want to change from one state to the other, it's really like an activated process. So I have to make a jump from one phase to the other. It's very different from critical phenomena in which I have states which are marginally stable, in which I have many soft modes, and in which actually I don't have an activation phenomena. Here it really looks like I have a barrier to go through, and the barrier scale with the system size to some power. So just to give you an example, I just finished, and then just to give you an example, if I take the Ising model below the critical temperature at Tc, I don't know, Tc divided by 2, I know that I have two phases. So a phase is plus and the phase is minus. And then what is the time scale to go from one to the other? Then is exactly, well, it's in that case, the time scale, let's say for Ising, is exponential psi, if I consider a box of length psi, to the d minus 1 with a constant in front. Okay? So here the idea is the same. I have phase which are stable. I want to go from one state to the other, from one phase to the other. So it looks like I really have to jump a barrier, and the barrier should scale with the system size. And well, this is an argument, and for the moment there is no way to compute psi, but I will discuss more this. Yes?
Yeah, why can't you make a transition by the motion of the barrier, just like in other sort of transition?
Yeah, so, well, so, okay. Can you put down the... So actually what happens is that what you want to do is you want really to change from this state to another one, because otherwise you don't gain configurational entropy. So it means that if you do this, then, and I mean, okay, let me just draw what I mean. So if I have, let's say, state alpha 1 here, then a state alpha 2 here, and then you say, well, what happens is that I could go from, let's say, here I have a boundary, and then this boundary will go here, okay? But now inside here, I have another state, alpha 3. So what you mean is that it's not the nucleation from here, but it's nucleation from there. So this is okay, it's just the same barrier. Instead, if you just move this and you just put the state alpha 2 here, then it's not good because alpha 2 is not chosen at random between all the states, so you're not getting. So you are nucleation again inside the one. Yeah, it could be inside or from the boundary, but it should be really different from all the other states.
Yeah, but I mean, this the psi dependency implies that the whole thing transforms. That's what
yes,
I thought that's what you said,
yes.
Rather than nucleation inside alpha 1. If it is a nucleation from inside alpha 1, once again, then it should not depend on the size of the region, right?
Yeah, well, it depends on side just because I know that if I nucleate another state here, just the argument that I gave before, I'm going to have a loss term. Remember, I have a loss term which is given by the surface tension, and I'm not to gain anything because the free energy is the same. So actually, when I do this, I'm paying energy. I'm paying energy. I'm paying energy until when I'm here. And when I'm here, actually, well, I have what happens is that when I'm there, actually, the idea is that then I will go to another state, then another state, then another state. Okay, so I will just tell you two other things. So we don't know much about the exponent, actually, analytically at least. But no, here is okay. So the exponent theta, it looks reasonable that should be equal or less to d minus 1, just because if you have short-range interaction, you don't really understand how it can be larger than this minus 1. And then the exponent psi, actually, we think that it should be larger or equal than theta. And this is just the idea that, well, what I have, sorry, can you put it down? It's okay. So when I go from a state alpha 1 to another state, let's say alpha n, so really I have to move in a landscape in which I know that, well, I know that this having a boundary here, it costs me an energy which is psi to the theta. So, well, and this is a low energy configuration because this boundary will be chosen in a good way. So actually, I will cross barrier which are at least high as c to the theta. So that's where this inequality comes from, which is not an inequality that we did, is the fact that psi is larger than theta is inequality which is already known in spin glasses. It's down. Okay. How much time? Nothing, or it's gone? Maybe if I have 3 minutes, I conclude with the difference from Adam Gibbs. Sorry, and then we will continue tomorrow. So, so now while we have done all this description, so it's a very, I would say, it's a hand-waving description, and I will try to be more precise tomorrow and to tell you what one can do with this description of the mosaic state. But just before concluding, I would like to tell you what is the difference between this and the theory of Adam Gibbs of cooperative rearranging regions. Because it looks like there is, of course, some relation, but they are clearly different. So let's do Adam Gibbs in 3 minutes. So Adam Gibbs, what they say is that the system is divided in cooperative rearranging regions, which, and then, well, if you take a cooperative rearranging regions, let's say that have a size, again, that I will call psi. So what they say is that the cooperative rearranging region relax on a time scale which is exponential psi to the d divided by the temperature. okay? And well, it's called cooperative rearranging region just because, well, it's the length over which all the particles have to move together in a cooperative way to make relax the system. And then again, as in the mosaic state, you think that there is a kind of extensivity property, so you can think to the system as independent blob of side psi. And then the other thing that you do is that you tell, say, what is the value of the configurational entropy? So what the configurational entropy S of C, so let's say the number of states in which the system can be is equal to the number of states in which one cooperative rearranging region can be, n, to the power the number of rearranging regions, which is v divided by c to the d, okay? So this means that this is equal to exponential of log of n v c to the d. And then, well, you have to tell something, so you have to tell how many do you have. So let's say that you have a finite number, whatever it is. I don't know, 2, for example. You have a finite number of way in which the cooperative rearranging regions are. And so this is a number, let's say n equal to 2, so it's log of 2. So from this, what you get is that as the configurational entropy is proportional to 1 over c to the d, okay? And now, well, now at the end, what I get is the time scale. So if I just use the expression that was above, so the time scale, we say it goes like exponential c to the d divided by the temperature, which means exponential 1 over t times the configurational entropy, okay? So this is, well, Adam Gibbs. Now the difference with the, so you find something which is similar, you find exactly as I found that the time scale increases because the configurational entropy goes down, but there are some difference, of course. So, I will tell you what the difference are. So the first one is that you assume that you have this kind of relation, so tau, which goes like c to the d divided by the temperature, which is probably the worst thing that can happen. Actually, it cannot grow as fast as faster than this, and what we think is that it should grow less than this, well, less than this. With the time scale shouldn't go like exponential of the volume of the blob. But the important thing is that here you see here you think that the number of, let's say, of possible configuration of the blob is finite, and so what you find is that the configurational entropy. So if you look to a state of the system, what you have is that the state looks like if it was in a mosaic state, but, well, it's a mosaic state in which you have, let's say, 2 tiles, for example. So it's really different. And also the fact is that what determines this length is not really, well, the competition that I discussed before of entropy time versus the surface tension. So I think I will stop here, and then tomorrow I will discuss the other things about the story. Thank you.
No, not by your presentation, but by the theory. If you could show again I think the word mosaic or even the word microphase separated system is pretty bad, because it seems to imply that that's actually what I had in mind, that you have a fixed pattern of tiles. Whereas one should think rather of a system, of a correlated system like the Ising model just above the critical point, where you can divide the system in correlation region, size of the correlation length. But of course, you have one pattern, but you could as well displace your pattern, and it will be just as well valid. So it's not as if you have tiles that change their identity of states, but you can just, it's a grid, in fact, that you put on top of your system, and any choice of the grid would be as valid as the other one. Is that a good description, or am I also still confused by saying this?
Well, so there are 2 things, I think, in your comments, or maybe even more. So there is one, which is the fact that the mosaic evolves. So it's not good. So it's not good to put alpha 1, alpha 2, alpha 3 just because this mosaic is evolving. And then the other thing that you are saying is that actually there is no difference. So I put a grid saying here I have alpha 1 exactly in this region, and here I have alpha 2 exactly in this region. And what you're telling is, I think, if I understand well, what I call alpha 2 could be another thing, which is putting the boundary in another place. Is it right? this,
what I'm saying is that I putting the grid in that way,
Yeah.
and I decide that this is alpha 1, alpha 2. And if I displace my grid
yeah,
by 1 nanometer or I don't know, a fixed thing, I would have a good description of the system as well.
well,
So there's no mosaic of the system. It's just that the mosaic is my choice of dividing the system.
I think, well, I think the answer is, I don't know. So I will tell you tomorrow a way in which I can, a Gedanken experiment such that it could be that you are wrong, meaning that I will tell you the way in which you can compute alpha 1, alpha 2, alpha n, and then look where alpha 1, alpha 2, alpha n are. So this is a possible way. And the other possibility is that you are right. There are no well-defined boundary. There are some, there is no really difference between alpha 1 and alpha 2, and there is just let's say, the fact that the system is quote-unquote rigid over of this length psi, and then it loses rigidity. Rigidity, I mean not mechanical rigidity, I mean rigidity of correlation over this length. So it's different. There are two different options. I don't know which one is right, but.
But in your scheme, then there's no interface energy. If it is just a fluctuation, there's no interface energy. He assumes finite interface energy that plays a major role. So the coherence is not homogeneously or random, but it's inside the
Yeah, but I think it could be that there are no sharp interface. So actually, it's only when you look to the system between, let's say, R and R plus psi that you really see that you are losing this term. I mean, it could be that there is no domain wall, it's just something which is changing slowly, which is not exactly what I described, I agree, but it could be. But would be different, and indeed, I mean, yeah, okay.
Sir, I think I missed out something. Where is the fact that there is that the Hausmann temperature excess comes up in the relaxation time for the derivation of the relaxation?
Say it again.
Where is the fact that there is a TK in the?
Yeah, so exactly, this is a good point actually. So we don't need a TK actually. So what you need, in all this description, you need that there is a configurational entropy, and that the configurational decrease, and then, you can or you cannot accept all this argument, but you get a relation between the time scale and the configurational entropy. So what you can get, it's what, for example, Peter Wallin has said many times, is that, let's say that I plot temperature as a function of, configurational entropy as a function of temperature. So what you see, let's say in experiment, you see something like this, and then the system falls out of equilibrium. So you don't know actually if this is going to zero, or this is going, it's going to zero at a finite temperature, or it's going to zero at zero temperature. You don't know. But in a sense, you don't care. I mean, if what I have done is right, which probably is not, and there are many, many difficulties, but if it was right, then if I can really relate the time scale to the configurational entropy until here, this is what I've measured, and that's okay. And then, it's a problem for, let's say, a theoretician that would like to know the answer whether the phase transition exists or not. It's a phase transition that I can never measure in experiment. So it's not crucial. Of course, one should try to explain why it has this form. I mean, if it goes to zero, why just not go to zero this way instead of doing this funny thing? But yeah, exactly. It would be random first order crossover in your case. Yeah. Yeah.
I think implicitly in this whole picture, you do assume that the configuration entropy goes to zero because the basis for the mosaic description is a mean field picture that is assumed to hold within limited domains where the configuration does go to zero.
So you want that it goes to zero, that's for sure, because otherwise the length does not increase. The fact that it goes to zero at finite temperature is not really essential.
No, but you assume in all this that you presented today, that the SC you're talking about is what you calculated using a mean field theory.
Yes, you're right. In the mean field theory, it goes to zero at finite temperature. But again, okay.
So you see this type of activated scaling in randomly rising zero temperature. zero temperature as a function of field, and that's because things are pinned by the random field. Is that analogy useful at all? In some way?
Yes, I think it's useful, and I will discuss a little bit tomorrow. And also, I think Chiara Camarotta will discuss it more. Okay, thank you.
Okay, so the ones going to ISC will leave in 15 minutes, as usual.